Starting with 12.1, because that was a while ago that we started back with 12.1. So what was 12.1 about? We began with a specific type of law, or Hooke's law, good. First thing was Hooke's law. And let's talk about this for a second, because I see that people still make some simple mistakes in this area. So, first of all, Fs stands for the spring force, not the actual weight of the object. Let's recall that. So let's think about a sample so we know what we're saying as we're doing this. So let's say we have a spring hanging from a ceiling, and there's a mass attached to the end of it. Now, if I tell you the mass is, 2 kilograms, that doesn't help you much unless you convert that. What do I need to know? If I know the mass is 2 kilograms, and I'm trying to utilize Hooke's law, I don't see mass in Hooke's law anywhere. Where is that going to come into play? Where would 2 kilograms come into play? Yeah. So right off the bat, if you're given something about a spring mass system, and you're not given the actual mass, then what you want to do is think about the fact that you might need to calculate the mass or the force depending on the scenario. So here, I would start by saying this. So that's the weight of the object pulling down. So if you're trying to utilize Hooke's law, you need a force. If you're given a mass, usually what that means is that the mass you're given is exerting a force downward due to its weight. Now, if this mass has this much weight, it means that it pulls down with this much force. So the spring pulls back up with this much force. Okay, so this is the weight pulling down on the object. The spring, and technically speaking, it would be a negative, right? Because it's pulling down on it.
For this one, you were only given the mass?
Yeah. So say you're given the mass. Now, I'll go into more detail, but I'm trying to go one step at a time. So if that's true, if this is the weight of the object pulling down, it means that the spring force would really just be the positive value of that. So if you're going to try to utilize something with springs, I'm noticing students doing this a lot, and they're confusing the difference between Hooke's law and our period formulas, where we have 2 pi root m over k. Just because you're given the mass does not mean you have to use 2 pi root m over k. You might use the mass, which causes you to find the weight, which is then equal to the spring force pulling back up, and you could utilize this formula if you were given something else. So if I asked you to find the spring constant, what other piece of information do you still need? If I said find out what the spring constant is, you need the displacement, the change in length, or the change in the distance. It's fine, that's okay. Okay, the change in length of the spring that it undergoes due to this force. So if I told you that the spring is normally like this, all right, and the spring length without any mass attached to it, so this is technically emptiness, there's no mass there. I should just put a little dot instead. All right, the spring length by itself before mass is attached to it is 4 centimeters. And then a mass is attached to it, and the spring length is now, instead of 4 centimeters, 9 centimeters. What's x there? Good, Kian. Okay, so x is definitely 5. And I know that it's down, so it's negative 5.
And you'll give us a diagram with.
So it's either a diagram or it's like a word problem, one or the other, yeah. Either you're given a diagram or you're given a statement. So if I were writing this into a word problem, here's how I would write it. I would say, the free length of a given spring is 4 centimeters. When a mass of 2 kilograms is suspended from that spring, its stretch length is 9 centimeters. Based on this information, determine the spring constant.
So you don't give it to us.
Okay, so I'd be giving you, again, I would tell you that the free length is 4 centimeters. When a mass of 2 kilograms, I'm not giving you this, when a mass of 2 kilograms is hung from the spring, its length is now 9 centimeters. From this information, find K. So you're not given any of this, but you're given this, you're given this, you're given this, just in words. All right, based on the 9 and the 4, you subtract the 2 to determine that the spring has been stretched 5 centimeters downward. Now, in addition to that, based on the mass, we come up with the weight of the hanging mass, the actual weight of it. The weight is pulling down, so the spring force is pulling up, equal and opposite to that weight. So we, as a result, have the spring force, we have the displacement in centimeters, we can determine the K value. Now, if this is well, it wouldn't be a multiple choice, it'd be too much math. But technically speaking, you could leave it how it is, and your units for K would be newtons per centimeter instead of newtons per meter. Okay? But if you're using the period formula, the values need to be in standard units. So it's up to you. I don't care really which way you do this. So solving for K here, you get Fs equals, or Fs over negative x is equal to K. This was from our lab also.
So as soon as you find Fg, the positive answer would be equal to Fs?
Correct. Because Fs pulls upward, so it's positive. Fg pulls downward, so it's negative.
And then from there you can just solve for it. And you have to just find that.
Yeah, but you can just plug in at that point.
Wouldn't Fs then be negative because Fg plus Fs equals 0?
No, because Fs is pulling up. I'm just looking directionally only. Only directionally, okay? So I'm looking at Fg as a negative. I call that negative for down, so then it's positive. But recall here, guys, look, x is negative. So you're going to end up with a negative negative, which is a
Positive.
and thus giving K positive. The whole thing is, again, K has to be positive. So as a result, I can either plug in at this point and leave it with centimeters or convert it to meters. But if I convert it to meters, then my units are newtons per meter. If I leave it in centimeters, my units are newtons per centimeter. It really doesn't matter which way you give an answer, okay, for the K value. It makes no difference here. But if a problem was given with a K value listed as newtons per meter, you have to then convert that to meters because it's in meters already. But if you're not given anything with meters, you could technically leave it. If you want to be safe, always just convert to meters. Good.
Is x always going to be negative for these types of problems?
If something is hanging, it's always going to be. If it's left to right, it can be negative or positive. Okay? Because again, hanging mass is always acting down. That's why that always happens to be negative. But if I told you a spring is stretched to the right by a force applied, then x is positive. And the force backward from the spring pulling back is then negative in that case.
Do you have to switch to centimeters or can you just put it in?
No, again, you can leave it in centimeters, then your answer is in newtons per centimeter. Okay, and the answer will be different by a factor of 10 or 100. 100. Kian, what do you got?
It's
So if you were in centimeters, you would have 3.924 newtons per centimeter. All right, because you're dividing by, if you left it in centimeters, you're dividing by 5, which means you're dividing by bigger numbers, so this is to get smaller. By how much? 2 spots.
We can't say negative k is equal to.
You could, but that doesn't make sense. At the end, you have to divide by the negative. You would never say negative x equals negative 7. You would say x is 7. But technically speaking, mathematically it's right, but you're not coming up with the actual k value. You're coming up with the negative k value. All right, now let's talk about this for a second and talk about relationships here. So, if it takes more force to do the same stretching, what could you tell me about the k value? If it took more force, it's a higher k value. Remember, the k value is really a rating. The k value tells you how much force it takes to stretch a given distance. If it takes more force, it means you have a stronger spring or a higher k value. It has nothing to do with the geometric properties of the spring. I shouldn't say nothing. For the sake of this class, it has nothing to do with it. So you could have a spring, like in the lab, the spring with a larger diameter had a lower k value because it was more flexible. Okay, which is a little bit counterintuitive because students have the tendency to say bigger spring, bigger k value. It just means a higher k value means a stronger spring. Stronger spring. A person could be twice the size of another person, yet be weaker than that other person, right? Think about it. Size doesn't necessarily mean that the person is stronger. Same with the spring here. Okay, so in this case, it matters how much force is really applied. Right? How much force is applied. Let me think of what else I want to ask for this. I have some ideas I wrote down. All right. Here's an interesting one for you. Yeah.
You said it takes more force. Like if it takes more force, then the K value will be higher.
Correct.
More than what?
So, like for example, if it took instead of taking this much force to stretch it, if it took like 30 newtons to stretch it the same exact distance, this value would have to go up. So it'd be a stronger spring.
You tell us it took like 30.
Sure, or a larger amount, whatever it may be. The number's arbitrary.
Yeah.
It's the constant.
So increased force, increased K value.
If it takes more force to stretch a spring, it means it's got a higher K value than the other one. Correct. So you compare two springs, you stretch them both the same distance, but it takes a lot more force for spring A to stretch than spring B. It means spring A is a higher K value, or it's a stronger spring. How would you show me a graph of this? What would a graph of this look like? Of spring, force versus stretch.
What this is if like the applied force is, or if something has to be constant here, right? Like, all right, so if the force applied.
Yeah, let me say force applied instead of spring. Actually, that's a good point. Go ahead, keep going.
Right, and then if K is.
Well, K's not involved yet. Well, we'll talk about where K comes into play. But graphically, think about this.
If the force increases X.
Very good.
Yeah.
As the force increases, X increases. And think about it. You apply more force to a spring, what happens? Stretches further and further and further. X is getting larger as F gets larger. So they are directly related. We know that from Hooke's law. And we know that Hooke's law says this. Now this is Hooke's law here, right? Negative. But we know this is the applied force. I'm going to call this applied. The applied force is just positive Kx, okay? Again, remember, because the applied force and the spring force are opposite each other. So if you wanted to write an equation with the applied force instead of the spring force, just get rid of the negative. It's the opposite of it. So look at this. It makes sense. This is like, ready? Y equals mx plus b. What's b?
Y-intercept.
And what is it physically?
0.
So you notice that the y-intercept is the origin. You notice also that x is the independent variable and f is the dependent variable. So look at this equation. What can you conclude about k? K is the blank. What is it? Slope. Awesome, Kian. Very good. The slope of this graph is what k really is. And think about that. Common sense. You increase f, you increase x. So they're directly related. That's the first part. Then you know that Hooke's law tells you that Fs equals negative Kx. So if we're looking at the applied force here, this is really m. Y equals mx plus b. This is m, so this is really the slope. This is really the slope. How would you draw a graph of... Ready? I'm going to tell you a scenario. I want you to draw me a graph. A force is applied to a spring, and that force increases at a constant rate until the force is held constant. Well, actually, let me think for a second. Actually, hold on, I have to reword this. I'm sorry. Let me think. Hold on. Okay, I got it. So. And I wouldn't be able to work that way. Forget the question, because I'm thinking of time, and you need a z-axis to plot time. It wouldn't even work. Yeah.
What was the name of this graph? Like force versus graph?
Force applied versus displacement. Force applied versus displacement. I'm trying to think of an alternate way of wording this. Oh, all right, here we go. This is how you can do it. A force is applied to a spring, and the force increases at a constant rate. It's the same beginning as what I said. And then the force decreases, and then the force decreases until the force applied compresses the spring. Again, a force is applied to stretch a spring, and the force increases at a constant rate. Then the force decreases until it compresses the spring. Draw a graph of this behavior. Do you need the wording repeated, or are you confused? Which one? Some others before I give you an answer.
The bell graph?
That's what I'm hoping you guys can figure out. So tell me the beginning piece. Give me the first half.
Just straight up.
All right, so definitely this to start, right? We know that because the force increases, and then it says the force decreases,
So it goes down.
okay, until it is being compressed. So how far should I go?
All the way.
To here?
Yeah.
And should I stop?
No.
Thank you, Julia. Why do I have to go below the graph at the end?
It's compressed.
It's compressed now.
Oh, negative.
So you'd have a negative force in that sense, right? If you apply a positive force, this is force applied, not spring force. If you apply a positive force, you get a positive displacement. The only way to get a negative displacement or a compression is to apply a negative force. So once the force is negative, okay, we're going to end up with a compression in this state. And this would actually be, I gotta change the shape at the end here. So this shape is going to get a little bit funky. It's going to decrease until it gets to there.
How would you get it just to stay at 0? Like where it is right now?
Hold on one sec. See, this is the problem. This is why I'm misleading you guys. I'm graphing this as a function of time. That's what I said a minute ago, why the graph would be confusing. Because if this axis here, if this were time, this would be correct. But this is not time, so this should actually not look like this.
Can we expect a graph in the test one?
You could expect to be able to apply some graphical knowledge of what we've been doing, for sure.
It's like that.
I'm trying to think of how I would word it. So for a question like the one I just gave you, I would make it a word problem because you really actually can't graph this. You would need well, here's what you would need. You need a third axis, and you need like a z-axis which plotted as a function of time. But we haven't done anything like that. So let's just leave it as, if I asked you that as a word problem, how you'd be able to respond. And what Julia said is correct, the idea. So if you apply a force that continues to increase, the stretch will continue to increase. Then if the force decreases until it's compressed, eventually that force will get lower and lower and lower. And when the force is negative, then it compresses. So to reiterate, here's the wall, here is the spring, here's the force. You apply a force that gets larger and larger and larger, causing this to stretch further and further. Then you decrease the force, causing it to go back to equilibrium, until you then have compression. And when you have compression, then the force being applied is negative. Okay, the graph is just throwing it off, so don't try to ignore the graph for that.
There's no graph. It's not the bell graph.
We have to read graphs.
What I just did there, ignore the graph. But you should be able to interpret graphs in general, like all year we've been doing.
So if an applied force increases, then
Stretch increases. As applied force decreases, stretch decreases. If applied force is negative, then it's being compressed. We talked about some terminology. We talked about some terminology in that first section for simple harmonic motion. One of the things that we talked about. What did we talk about? Okay, the word oscillation. Oscillation, what does that mean? Good. Same word as vibration. Oscillation, vibration are the same thing. It depends on if it's a spring or a pendulum.
this is still 12.
Yeah, either way.
Yes.
Still 12-1, yeah. Still 12-1. Did I give you any other formulas in 12-1?
Just one.
Just Hooke's law? Was that all 12-1 was, Hooke's law?
Yeah, the two pendulum and spring came
Yeah.
together. 12-2, I think.
Okay, for the period part. Good.
Then for the example that you've given here was x equals x3 minus x.
Yeah, which is just the difference, exactly. But that's common sense. Go to the next. Okay, good. That's what I want to do. Kian. 12-1. Finish up with 12-1 still. So there's some terminology for springs and pendula that are analogous to one another. So if a spring looks like this normally, and then a force is applied to that spring, causing it to now look like this. We call this, and imagine it's released and this thing starts to oscillate back and forth. What do we call that max stretch? What's the word for it? Not F max, no. What is the maximum stretch? You let go and then, ready? So I stretch. Let me give you a demo of my hand. I stretch this, I let go, and this is going to go like this, right? Eventually stopping, energy dissipating, coming back to equilibrium. The stretch that I pull with and let go, what is the word for that? Displacement is one word. Good. What's another word? Think about the words we were using for like the waves and stuff. Not the period. The period is the time it takes. Remember, the period is the time it takes to oscillate once.
A name for when it stretches and then comes back.
No, the name for the actual stretch. She used the word displacement, which is right, but there's another word for displacement. It also is maximum displacement, but there's another word completely. What is it? Amplitude. Very good. So remember the word amplitude for waves. Remember with a wave, it was the top of the wave and the bottom of the wave? That's the amplitude, really, is the stretch, how far it's stretched. It's the same thing as a pendulum. So here's your pendulum. Here's the vertical. For springs, the amplitude is the x value, right? For a pendulum, what's the amplitude? We did this in the lab.
Symbol.
Yeah. What's the word then? Forget the symbol name. Just what's the word? The what?
The way no.
Now you're just throwing random symbols out there. You're on a roll, Kian. Don't abuse the roll. What is it? Nobody?
No, I know it. That's it.
For a spring mass system, the amplitude is represented by x, how much is stretched. For a pendulum, what's the amplitude called?
It's not just capital.
Think about them. They're analogous. For a spring, it's how far you stretch it and then let go. For a pendulum,
It's how far you hold it in there.
so what's the actual thing that represents the amplitude? Not the length,
Frequency.
not the frequency.
The pendulum length, it's not the.
Here's the pendulum, right? Ready? All right, look at the
The
pendulum.
mass of the pendulum?
Small amplitude,
Oh, the
larger amplitude, larger amplitude. What am I measuring?
The degree.
What's the word then? Not the degree. The angle. Thank you. And were you trying to say theta? Is that what you're trying to say or no? Okay. I thought you were saying theta. This is the amplitude. Ready? Watch. You take a pendulum, you raise it up to its max amplitude, let go. What does it do? It does this. It swings from one amplitude to the other. Just like a spring, ready? Here's the swinging pendulum. Here is the oscillating mass. They are literally the same thing. I keep saying this to you guys. They're analogous.
What is it?
When the spring is at its max amplitude here, stretched, it then comes back, the spring hits equilibrium, same time the pendulum hits equilibrium. Then the spring goes back, it gets compressed as the pendulum moves up. So the motion is identical. This is left to right or up and down for a spring, whereas this is angular. So a pendulum is a rotational representation of a spring. That's all it really is. A pendulum is rotating like this, right? Or oscillating or vibrating, or a spring is oscillating or vibrating linearly, not rotationally. Okay, terminology is important. So let's keep going with terminology then, since we started that. Somebody mentioned the word period. What is the period for both of these systems? Tell me. How do you know the period for a spring mass system?
The time it takes to start at one position, go past equilibrium, and then come back.
Very good. So for a spring specifically, as Cooper said, it gets stretched all the way to here. It's released. Okay, the spring does this. It passes equilibrium. It compresses. And then it comes back. It will keep doing this over and over. The time it takes to do this once is the period tau. Okay, that's the time it takes for one cycle. So for a pendulum, what would it be? That was for a spring. Kian, for a pendulum.
I'll do that one.
Yeah, so starting up here,
Yeah.
like this.
Yeah, back and forth.
Yeah, very good. Back and forth. Well, that's good. So back and forth. That's one period length of time for a pendulum. What is the word frequency? What does that mean?
A spring, it's when it's stretched, compressed, and back.
So it depends on how you start it. If you start by stretching it, right, then you have let it go, it compresses, and then it stretches. That's one period. Or if you started by compressing it, then it expands and then compresses. That's one period. It's the same thing. It's like remember the graph? It was crest to crest or trough to trough for wavelength. Same thing for period. It's either from the compression back to compression or from extension back to extension. It just doesn't matter. It's either one.
Pendulum goes up and down?
Yeah, because pendulum, you start here and you do this, or you start here and you do this, but it's the exact same thing. So that was period, right? What is frequency? Omega, good. So we'll start with that. But what is it now, Cooper?
How often the periods occur?
Correct. Or how quickly the cycles occur. The amount of cycles per time period. The amount of cycles per time period. So high frequency means quick vibrations. Okay, low frequency means slow vibrations.
This is 12 2.
This is a combination of a few of these sections actually, yeah. I think it was part 12.2 and 12.3 there.
Wait, so higher the frequency, the higher the...
Oscillations, how fast they move, yeah. Alright, I'll give you a quick example. Has anybody ever used something called a water pick? I know it's a random thing, but have you heard of this? You know when you like floss your teeth with floss?
Oh, yeah.
Okay, you ever go to the dentist and they take water and they spray high frequency water between your teeth to clean out when you're at the dentist? Well, you can get these things at home now. So I actually have. I like to keep my teeth nice and clean. So I use one. And they have, it does keep your teeth real clean. They have different frequency settings on the motor. And what you do is if you change the high frequency, the water comes out faster because the motor is spinning quicker. And you hear it change. You hear like the higher frequency. If you've ever been at the dentist, ever get a cavity filled, you can hear the frequency change. Okay, it means that the motor is spinning faster. So the more cycles, the quicker it spins, or the more oscillations, the quicker it vibrates, is higher frequency. That's what it is.
That's how you brush your teeth?
No, you brush your teeth normally. It's for flossing instead of flossing. It does like a 10-time better job than flossing does. It's unbelievable how much more it gets out. It really is weird, but it works well. You ever leave the dentist and you're like your teeth feel so clean when you leave the dentist, right? It's the same feeling when you use like a water pick too. It looks like a little stem with a little spout at the end. It looks like the little ones at the office, but it's plastic instead of metal. You fill like a chamber of water up, you charge it, turn it on, and it pumps the water out at like a really high speed. It's really, really fine, the tip. So it's a little stream of water. It just shoots it between your teeth. It's useful. All right, back to physics.
I'm sorry, what was the higher frequency? It's quickly
Rotating or oscillating or vibrating, any of those words. Johnny, please leave her alone. She asked you nicely.
What's the next number?
Let's see. You should be able to know the difference between constructive and destructive interference depending on like the scenario. Constructive means
Gain, addition.
it gains, it adds. Very good. Destructive means they're two pulses canceling one another out. Hey, cancel.
Can you give us last night it said when can it increase and that's for the
If both of the waves are positive amplitude or if they're both negative amplitude. Because if they were both negative, it would increase, but in the negative direction.
Sorry, can you repeat what you said about constructive and destructive?
I didn't say anything. He asked the question.
Can you give us real life examples of both?
Remember the two wakes coming together? It's the simplest way to think about it. Imagine you have two wakes literally coming together at the same time. There'd be a higher wake in the middle.
We're not going to answer think of it.
The idea is what I want you to know from this. It's really, again, it's one of those topics that until you study like electricity and magnetism, it's not really useful. Okay, so I'm trying to get you the gist of it.
What are the pulses added to when you have constructive or destructive interference?
What do you mean?
What do you mean?
I don't know.
She said that constructive was that pulses were added and destructive
The amplitudes are added. The amplitudes are
are
added
added to what?
to each other.
Oh, to each other.
Hmm? The height of the wave.
Amplitude is height of something?
Amplitude is always the height of something. Same thing here. Look, Jack. Technically, this is the amplitude. It's the height or the stretch. This is like the height or the angle there.
Oh.
It's the distance from the norm. So if you were graphing something like this, right? A wave like this has a positive amplitude. It's a pulse wave in the middle. The height of that would represent the actual amplitude. Say this height was 5 centimeters or whatever the wave height was. Be able to understand, we talked about amplitude being related to one another. Remember we said this? That
Squared
the energy, yeah.
is amplitude squared.
It's proportional to
It's got that weird sign.
Yeah, proportional to, which is this sign.
Yeah.
It's not really equal to because there's a bunch of constants there. So think logically about this again. You're going to have to definitely answer this with words. And maybe in addition to that, a multiple choice. But the idea behind this is the following. The higher the amplitude, the more energy the system has. And then use logic. Why would an object stop moving eventually? Because it loses energy to friction. And therefore its amplitudes are decreasing. So you take a spring, you release it, the spring oscillates, right? Like this, back and forth. Eventually what happens? To
Friction.
friction and whatever other losses there are, not gravity. Just friction and air resistance. So if it's losing energy, it means it's losing amplitude.
Oh, okay.
Okay? That's why it eventually stops.
So they're
When
like
it stops, what's the amplitude then?
nothing. Zero.
Zero.
So they're like
It's a more
directly
energy,
related
more
to.
They're proportionally related to the square of one another.
The higher amp means.
The energy is proportionally related to the square of the amplitude. It is direct, but it's direct to the square, it's called.
I just want to make sure that I have this right. So with destructive interference, because they're on opposite sides, I mean, I don't want to say the x
They
axis.
cancel each other out.
So that there's no combination.
Of what?
Because with constructive, it combines into one big wave, but with destructive, there's no way that it can combine at all, right? Because they're on opposite sides. They just,
No, they do combine, but they cancel each other out. So if this one's 5 and this one's 3,
They just switch.
5 minus 3,
No. It comes in the middle.
2.
Oh, so it's just.
So that's what we
Sum,
just did.
superposition. Remember the
That's
sum
I
of
think
the two
so
waves.
that the final wave would be.
This is what we just did, isn't it?
When they pass each other, the wave would be 2, and then they would separate again and continue past.
But that's destructive.
Wait,
right?
does this
Yes.
have to do with wave like this, what we just did?
more energy, more.
Is it the more?
More energy, more amplitude. Yep. Yep, that's right.
Constructive and deconstructive is this though, right? When you find them resultantly?
It's that, and it's also, go back. Oh, no. Go forward, no, forward.
Or
Other way.
other way?
You went too far back.
Say the whole class.
That first one, too.
This, okay.
The diagram, the first diagram.
Gotcha.
All right. Let's see what else.
Yeah, there it is. You understand? I hate it. It's really nice.
What is the difference between transverse and longitudinal?
Oh,
Transverse goes perpendicular and up and down to the pulse.
Good.
And then longitudinal is parallel.
Yeah. So the wave, imagine a wave is moving left to right. If it were a transverse wave, the molecules are vibrating vertically then. If it's moving left to right and it's longitudinal, the molecules are vibrating horizontally also. Okay, so again, it depends on the direction of the wave. For longitudinal, the vibration is parallel to the wave direction, whatever that may be. For transverse, the vibration is perpendicular to the wave direction, whatever that may be. So it really depends on which way the wave itself is moving.
so if it's like a wave up or down, the molecules are.
We'll be moving left to right for transverse.
And if it's a horizontal wave, then the molecules are moving up and down.
For a transverse.
Transverse only.
Yep. Both those examples were transverse, Jeff. And the vibrations are parallel, not perpendicular there. That was the big key that we talked about. You should know what the word superposition means, okay? The general definition of it. And the idea that the two sum of the waves becomes the third resultant wave. Alright, superposition was the interference part. So the sum of the two amplitudes is equal to the resultant. Alright, so if you had this, ready? I can give you any graph and tell you that this is the, let's say that this first wave is represented like this, and the second wave is represented like this. Alright? And the question said, what would a resultant wave look like from these two? Well, if these are the original waves, you have to sum them together. What would be a good way to figure out what the final wave would be? Yeah, give yourself some axes or some sort of number marking. So if this is like 10 for now, this would be 20 up here. This would be down at around -10. Follow what I'm saying? Give yourself some sort of reference point. Now, if you had to completely draw a third wave, that would be a little tricky. I might give you 3 waves and ask you to figure out which one the resultant is, like we did yesterday. But if you were to add them together, it's not that bad. Ready? So here, add 0 and 0, you get
0.
the whole way through, though, as this goes up, this goes down. So what are you going to stay with?
0.
It's going to remain 0 until you get here. Then it still becomes 0 up until you get to right here, maybe. Now, at this point in time, the height of this wave is like -3. The height of this wave is like 5. So this is going to spike up. Okay, then eventually you have no height of this wave here, right? There's no height here. Yet the height here is about 5, so 5 plus 0 is still 5. So this is going to hike up until you get to here. Then, after you cross this point, what you notice is this. This wave starts to become positive. This wave is also positive. So this is going to keep increasing. Now, once you get the sum of these two, it's going to be flat for a while. This is going to be flat still here. Because again, in this region, this wave is 5, this wave is 10, 10 plus 5 is 15, and since these are both constant at 5 and around 10, this is also constant. Eventually, it's going to move back down. So let's see, next it would be, let's see, this shoots up, so this has to go up once this gets here. Let me erase this piece just a little bit right there. Or can I not do that? Of course I can. Hold on. Use white ink instead.
There it is.
All right. This would continue up here until this one began to decrease. The other one was constant. So this would continue up. And this would eventually come down until you got to the end where you were pretty much steady. When these are, actually no, this goes down until you get to here. And then it would be steady the rest of the way. So take a look at the black wave. I know it's tough to do this. I'm going to ask you to come up with which one the third wave is, or maybe I'll say at an instant in time, what is the resultant wave? So you can put that vertical line like we did yesterday. So put a vertical line anywhere now. So take a vertical line and slide it back and forth. So let's take a look at this to show that this is true. Can you give me a sec? I see your hand.
No, I was stretching it.
Oh, all right. That's even better. So this vertical line here, right? If I pick any instant in time, like right here, if I sum together the red wave and the blue wave, I should get the black wave. And it makes sense. The red wave is up at like, I don't know, 18. The black wave, maybe it's like -5. So the blue wave has to be less than the red wave. You're taking, ready? If I said, let's say this is time. All right, and I said to you, at time equals 15 seconds, which is where the vertical line is, determine the height of the resultant wave. Well, if this height is around, we'll say 18, and this height is around -7, the height of the resultant wave should be 11. Okay?
Wait, what's that black one called again? Is that that's the superposition, right?
The vertical line?
The black, like the line that you
The resultant wave. Resultant.
So it doesn't really have to be like halfway between the two, you would say. So
No, it could be anywhere, yeah. So like at any point in time, maybe you have to find the height of the resultant. And all you got to do is put a vertical line. So let's say after 7 seconds. 7 seconds, I go over to 7 seconds, I put a vertical line. This height is about 5, this is about 9. 5 plus 9 is? 14.
Alright.
All right. We're going to just all make believe didn't happen. It's okay. Anyway, the idea of superposition is that the sum of the height of two waves equals the resultant wave. All right? The sum of the two equals the resultant always. Let's see.
What lesson are we on now?
Are you over the two equations?
I'm kind of jumping around. Yeah, let's go to the two equations, which was lesson 12. Well, there were 3 equations there.
Oh yeah, it is.
Sorry.
He used my cell.
Did I write the first one correctly, or did I write it the other way for you
It's
guys?
W equals 1 over time.
Okay. Just to be consistent with your notes. It's the same thing, obviously. All right, so what does the first equation tell me? What does it tell me? Cooper?
That,
You had your hand up.
1 divided by the period will give you a wavelength.
Not the wavelength.
I mean the frequency, sorry.
So what does that tell you about those two things?
Got their indirectly related.
Very good. They're indirectly related. If you have a longer time period for a cycle to occur, it means you are not having a lot of cycles occurring. So it's a low frequency. High period, low frequency. High frequency, low period. Okay, high frequency, low period. And the second one, okay, the second and third one. This is a spring here. This is a pendulum. Okay? If you study your problem sets and your homeworks for mathematical, you should be pretty solid for this. Also review your lab. Okay? Review it in Notability though, please. Don't edit anything and then post it in Dropbox or change that, because I still have to grade that lab. Okay, so review your lab. If you turn in a hard copy of a lab and you want a blank, just go online and download a blank. Or if you want a copy of yours, just come by and make a photocopy of it.
Lab 9 you're talking about, right?
Yeah, Lab 9. Lab 10 can help also for this, but, you know, a lot of theory.